Okay, so we're now on the air here. We're now recording. Let me share my screen. All right. Move this up here. What do we got today? We got 9 of us. And Caden. Now, Evan and Kate, well, Caden maybe not, but Evan, you ought to get yourself a little icon going, so, or your picture or something, so that if there's ever a question as to whether you were here, there'll be a recording of it, but what'll show up is not your name. It'll show up as a little shadow. So come up with an icon. So not that I don't know if they ever, if they're accusing you of robbing a bank, you can say, nope, I have proof. Okay. Corresponding with a student, an old student of mine, who's my friend now, and he's just about to lose his dad to COVID. And him and his dad were like this. I mean, I've known his dad too. His dad's an amazing guy. But you're on the last, he's ventilator for 2 weeks now, and they're about to pull the plug. So it's just a horrific time we're in. But let's not think about that for an hour, 45 minutes. He wants to come by and get some goggles so he can say goodbye to his dad. He's going to put goggles on, put the whole mask on, then he can go in and he can say goodbye. That's what it's coming to. All right, so this is Tuesday the 2nd, and this does affect you. Tomorrow, remember, tomorrow we're not meeting at 1. It's at 1. Sorry, not meeting at 1:10. It's at 1 o'clock tomorrow. So the bad news is it's 10 minutes before we normally meet. But the good news is we're out by 1:25. Now, I know it's Blue Day tomorrow in class, and I think I came up with an idea yesterday that I know I've already forgot what it was, but something about you all. Oh, okay, I know what we're going to do. You have a PDF of your test that I sent you, test 4A. So what I want you to do is print that out, or do a iPad if you want, if you have an iPad, but print it out. Correct. Redo 3 problems. I'm going to give you the key. I have your test. I realize that, the original test. But you're going to redo 3 problems tomorrow. And then you're going to PDF me that, I guess, or drop it off on my porch or something. And then I can give you half credit back. Now, you may decide, some of you are really bright students. You go, it's not worth it. And you're just going to but you still want to watch. So there's nothing new tomorrow. It's just all looking at that test and looking at how I work the problems and talk and have a discussion about that. So we can do all that in 25 minutes. Okay, now I gave you, I put a PDF of the take-home test 4B, just take-home test 4, in the, it's on the Facebook group. There's a PDF of it on Canvas. And then I just put some on my front porch. So if you want to get the paper copy, you can do that. But I put this picture, and this is also tonight, by the way. If you're going to take the ACT, we have tonight, tomorrow night, and Thursday night, and then I'll stop promoting, I promise. But this is our tutoring, our preparation. We've been doing this since 1995, so we know what we're doing. But this is through Zoom. Okay. Now, check this dude out. This is me back in 1978. And I am a little irritated at that point. My roommate took my picture, but this is as of 2 a.m. I think it was somewhere in there. It was early morning. I've been studying since about 6 the night before, up to about 2 a.m. So about 6, 7, 8 hours of studying for my first big physics test, because I heard physics is a booger, and so I was and I hadn't been paying enough attention. So I thought I could do as I normally do. I could wing it, and not wing it, but I could cram all that physics into my head. And this is mostly kinematics stuff we're doing. And I was I didn't have this is college, my first year of college. I didn't have any, so first or second year of college, but I didn't have any physics in high school. So this is a look of a irritated, exasperated, tired man. Or I was 19 or 20 at the time. I guess I was 19. And I was going through all these old photos, and I noticed this. I said, that my kids need to see this, because that is what I don't want you to do. I don't want you to wait on this take-home test, wait until Tuesday, a week from tonight, and then start it, right? That's disaster. Then you'll be like me. I went in the next day thinking I knew it all, and I didn't. I was confused. I didn't realize I was confused. And then I just bombed it. I got a D. I never had gotten a D on a test before, but physics ate my lunch because I knew math, but I didn't understand physics, the application of math. And so I didn't realize that just memorizing stuff didn't help. So you've got to, the point of this is you've got to do physics in little tiny chunks. Okay, so do a problem tonight on the take-home test. We have some other homework, but it's not due till Thursday. Do maybe 1 or 2 problems a night until then it sinks in. It has time to sink in. Anything beyond 30 minutes worth of physics on intense physics a night, you're wasting your time. I found that's one truth I've learned. And since this is 42 years ago, since 42 years, one truth I've learned is you cannot cram physics into your head. So that's my warning to you. Don't be this guy. Okay, so today we're going to, no, by the way, some of those problems on the take-home test, you can do the front side. That's all stuff we've done. You can do part of the back, but then after today, you can do everything but about 3 problems. And then we'll get those figured out Thursday and Friday. And then I think you could probably do the whole thing. So some of that you won't be able to do yet. It won't make any sense to you. So where we're going to go here. Let's look at, this is where we were yesterday. I think this is us. Let's see. Nope, this is us. This is us from yesterday, where we came up with this idea of this power rule, how you do them, and historically kind of where it came from. Hold on, I promised you something. I promised you that I would show you, and now I got to stop sharing the screen. Hold on. I'm going to see this. This is my wave generator, my standing wave generator. Okay, it looks like this. It didn't work for a couple of years. Now I got it working again. And the problem is it has to be dark. So I'm going to shut my shades. So bear with me. Bear with me for one moment while I shut my shades. Yeah, I get as dark as I can in here. It works better in my room because I have blackout shades in my room and I can get it real dark. Okay, that's the best I can do. Maybe you'll see it because you need lights. So this creates standing waves. And I know this doesn't have, it does have something to do with what we're doing, but it always does. You can kind of see the lights. So all this does is twirl these. And if you can, look at that. That's 1.5 waves right there. Can you see that? Is that coming through at all? I wish it was darker, but it's 1.5 waves. See, it's a sine wave, right? But that's what's called a standing wave. Now, this is what makes up, this is a string, and this is what makes up the universe. Now, it's called vibrating string theory. It's string theory, but it's vibrating strings. This is, if you were playing this on your violin, you'd get a nice tone, right? It's just because it's a standing wave. If you're in your trombone or your trumpet, this is what you're looking for, those standing waves, that resonance. This is called resonance, right? Now, if I speed it up, let me slow it down first. It's got these real pretty lights if it's night. Let me slow it down, see if I can get down to, I'm going to lower the energy. Remember, E is equal to H nu. So I'm going to lower the energy. The afraid of that. I can also change the wavelength or the like you do with the trombone slide. What you're doing there is you're changing the chamber, the length of the chamber. And I can change the length. I was trying to get in second hour the other day. I got beautiful. I got a half of a. I got one half of a wave, and I've not been able to achieve that at flash speed. Okay, and let's. Oh! There's perfect that. See, that is one wave. That's one sine wave, a standing wave. This point right here. This point right here that's not moving. That's called a node. A node. So in your microwave, these things set up. We talk about the marshmallows. This is electromagnetically what sets up in your microwave that cooks your food. Now let me crank the energy up. E energy equals H, which is Planck's constant, times nu, which is frequency. So if I crank up the frequency here, I crank up the energy. Go. Oh, I increase the amplitude, the intensity, but I want to get this. You just got to get the length just right. Pull that off. There we go. Now that's called destructive interference. That's like a sound wave. Sound waves are not, unless it's a perfect tone. Oh, it's setting up again. Now I have two waves, two complete waves. See that? Two standing waves. This is called a ground state. It's a low. Well, it's not the ground. The grounded state would be half a wave. That's as low as you can get. This also has to do with electrons in an atom. Am I taping this? Am I recording this? Yeah. Okay. So electron. I wish you could see it better, but this is like the n equals 2 level. These are called pilot waves. De Broglie called them pilot waves in the 1920s. And this is how, like on your Bohr model of the atom, n equals 1, that's one wavelength. N equals 2 wavelength. So you can't, if I go in between there, it ends up destructively interfering with itself every time it goes around. Okay, I doubt I can get 3, but I'll try. Crank it all the way up. See if we can get 3 out of that. That's no, two standing waves, the best I can do for this energy. We need to increase my batteries. Okay. So that didn't really fit the discussion. Give me a little bit of light back. So that didn't really fit our discussion today that much, but that's what I wanted to show you the other day when we were talking about waves. And we'll talk about waves again, probably starting Friday. We're going to work on 411, and 411 is the hardest sheet, I think, in packet 4. So I saved the hardest for last. All right. Oh, my lighting's not good. I gotta get my lighting right. All right. Crank this one up, and then let's get back after those derivatives. Okay. So let's go back to sharing the screen. Okay, there we go. Okay, we're back. So we did this yesterday. It's the origins of the derivative, looking at some practical application of balls rolling down ramps. Newton trying to understand what's happening instantaneously to that ball. Okay, I'm not saying he rolled balls down ramps. That was Galileo. But Newton's using Galileo's ideas and then going from average to instantaneous. And that's where this power rule is born. And you have to buy into this idea that that once you get down to the zeptoseconds or femtoseconds, that delta t is like if t1 is this number, if t1 is this number here and t2 is this number, those essentially, the difference is no longer delta. It's so small, we put a little d in there, little d, meaning little dt, tiny, tiny, tiny delta. And that difference is so small that we can essentially say they're the same time. Now, if you don't say that, you can't do this move right here. this crucial move in Newton's derivation of this, where we have T1 and T2, two distinct times, but he said once that becomes infinitesimally small, that difference, they are essentially the same time. Okay, so you have to believe me. I'm not trying to get you to believe that 2.00 is the same as 2.01. I'm saying, no, I agree. That is enough difference there. But when you get to the point where it's zeptosecond difference, then you can say, okay, come on, it's the same time. That's part of the way your mind has got to work when you're understanding calculus. And also, like I said, there's some chemistry stuff you can't do if you're not willing to buy into that stuff. Now, oh, write this down. This is probably good for your notes, so I'll give you a minute to write these down. On the left is Leibniz interpretation. In math class, if you're in calculus, your teacher will say LIM. And I remember, you'll write, I'll tell you a story while you're writing this down. I didn't understand. I was such a knucklehead in high school. I didn't ask questions, right? I mean, I always berate you guys for asking them questions, mainly because I didn't. And I just assumed that it didn't make sense. But the math teacher put LIM. What is lim? I never knew what lim was. And finally, I think a couple months later, I realized that's limit. Okay, so limit is the limit as delta t approaches 0, as that change in time, then that delta t becomes or turns into dt, little dt. So really the derivative, that's the derivative of x, but it can be derivative of anything. And really just for Leibniz, the symbol for derivative is d. If it's derivative with respect to time, it's d dt. And then you plug into here whatever you want. It could be df dt. It could be dx dt, right? Da dt. Anything you want goes in there. But that's telling you you're taking the derivative with respect to time. Well, that Newton shortcut, a good shortcut, it's a good shortcut way of saying it. If you are taking change, if you're, no, let me write this, let me do this nice. If you are if you are looking at, if you are determining change, instantaneous change, sorry, trying to make this better, instantaneous. I work extra hard with you guys because I know that this is the record. This is the official record. If you are determining instantaneous change with, here's the big thing, with respect to time. That is the limitation of using dots. When I write it as x dot, a dot, v dot, x double dot, it's really nice. It's simple, quick, but you are assuming that it's dx dt. Now, what if we do something like force? But I'm looking at how, and we're going to do this later on. And this is like April, but I'm looking at how force is changing, not with respect to time, but with respect to position, because I might have a position thing with force over force. I'll give you a little preview. For putting a force on something through a distance, that's called work, and that translates to energy. But I cannot say, I'm not saying with force, I can't say cannot make it f dot, because that would mean, and that's something else, that's a different deal. That's force, changing force with respect to time. But this is force with respect, so no, you can't use that. You can't, if If you're doing it with respect to distance, you can't do it. You have to use Leibniz notation, df dx, okay, or df dy, whatever. But that's a limitation of Newton. I have to then use Leibniz notation. So Leibniz notation, although cumbersome, is actually the better way to learn it. And I don't know if math teachers teach dots. Yeah, so let's keep going with that. So if I say the second derivative, like if I do a derivative twice, like for instance, let's say that x equals 3t squared, okay? Just a 3t squared, just a simple orange situation. Then dx dt, which is the same thing as x dot, is 6t, right? You just bring the 2 down in front and then take away 1 from the 2. All right, so we learned that yesterday. Well, if I want to take the next derivative, Newton would just say x double dot, and then you do it again, 6, whatever the units are. Well, I guess I'll be careful, put units. Say that's meters, then that's meters per second, and that's meters per second squared. Notice that the formula gets simpler, but the units have to make up for that and get more complicated. Well, okay, so how would Leibniz notation handle this? They would say d dt, which means I'm taking the derivative with respect to time, of dx dt, which is velocity, then that would equal d squared x dt squared. And there's another example of me in high school calculus thinking I knew everything, but really the teacher, Mr. Gilmers, would leave the room to go, quote, to the bathroom, and he'd actually go to smoke a cigarette because he'd come back smelling like smoke, but he would be gone for like 15, 20 minutes. And he'd say, before he left, he'd toss me the overhead projector and say, Asky, you teach. Because I understood I thought I understood the calculus really well. Well, I'm standing in front of the class as a high school student. My buddies, throw paper wads at you and stuff. But, you're still trying to teach them. And one kid asked me, so why do we do the d squared x d t squared? I couldn't answer. I didn't know. That's just what you do. I memorized it. That's what you do. But no, it's because of this, because you're saying d dx. Okay. So I'm trying to get it so that you're just not memorizing stuff. So there's a reason for everything. That's what I love about physics, is it explains every daggone thing in the universe, every physical thing. Okay. You can't explain love, but it explains everything that's physical. Okay, this was all brought up today in class. Just looking around, what else we got? Oh, okay, okay. Here's what I want to do now. Yesterday we did the left column. We did that. And then today on 4.9, I want to do the right column. So I'm going to, this is like you going to the board, and I'm going to put it on pause and give you a chance to work this. Well, before we do that though, let's look at this for a second. So here's my function. Notice that there's a cube, so it's a third order, and that cube means third order, which means for us pink. That is a pink equation, which means quartet. So this is called third order. So third order polynomials are quartets. It's a jerk, right? All this stuff goes with it: jerk, quartet, pink, third order. But that dominates. So it's not hard to do the function. Well, the function is just x of t, just write it down again. 4t cubed plus 3t squared plus 7t, and then units. I guess it's miles. Okay, so always watch your units. It's not always meters per second. But how do you plot that, right? How do you plot that? well, you put it into your graphing calculator, but let's say you don't have a graphing calculator. Okay, this third order, the fact that it's third order is going to dominate your graph. As t gets bigger and bigger and bigger, it's the cube that dominates. So this, just to let you know, this will be a cubic function. It's going to be right. It's 0 time x is still 0, so it's going to start there at the origin. It's going. If you look at if you plot this, you'll see in the first quadrant anyway, it still looks basically cubic. Now it comes down like this and comes around, but it starts at 0. Okay, so I'm giving you that one. Now what I want you to do then is the other. Give me 6 things. Give me the 3. Give me these 3 equations, and then give me these 3 graphs that go with those equations. Now, if you have a graphing calculator, you can, and I'll come back and talk about how you'd plot the x if you don't have a calculator. But go ahead and give it a shot. I'm going to hit pause and let you work for a few minutes off air here. Pause. So here we go. I think it's easier probably just do the equations first, right? So we go through here, and then these are all pink equations. And so we have x dot, which is v of t, then is, I bring the 3 down, blow this up. So I have 12t squared plus 6t plus 7 meters per second. Now, this power rule is something that everybody seems to pick up once you get good at it, and that's something, I don't remember anything else from physics, but remember the power rule. It is probably the best shortcut. I think it has to be the best shortcut in math. Let's do it again now for x double dot, which is the same thing as v dot, which is like dv dt, which is all these mean the same thing, acceleration. That then bring the 2 down, it's 24t. And then I got to put the units, that's meters per second. Oh, no. You guys didn't catch me.
Per hour.
Thank you. You caught it just in time. There's the point. It is miles per hour.
What happens to the 6 and 7?
Okay, hold on a minute. I don't know. I screwed up. Well, the 7's gone, but the 6 I screwed up. So there's 2 points there for correcting me. Plus 6. That's like t to the first, so the 1 comes down, and then the 1 minus 1 is 0. Now the 7, okay, hold on. This is miles per hour squared. But the 6, okay, let's take this. 6t to the first. Remember, a derivative is a slope. So you're saying what's the slope of 6t? Slope of 6t is 6. It's 6 whatever. And that's thinking graph-wise, but 6t to the first, just plain power rule-wise, 1 minus 1, so it ends up being, and t to the 0 is 1, so it ends up being 6. But 7, when I'm doing 7, well, if I have, what's the slope of 7? Well, 7's a constant. What's its slope? Its slope is 0. There is no slope, so it makes sense. But looking at it calculus-wise, that's like saying 7 times t to the 0 power. And then if I do the derivative, the 0 comes down front. And someone said, well, wait, wouldn't it be then t to the negative first? No, because once the 0 comes down front, it wipes it all out. That's just plain 0. I don't care what you multiply it by. So it's kind of cool. Power rule works. That Newton's a pretty clever fellow. So is Leibniz. And then we'll plot it here in a second. And finally, x triple dot is a jerk. Which is dA dt. I'm using both Leibniz and Newton. And then that's just plain 24 miles per hour cubed, which is not as big a deal as you think it is. All right, so now we go over here to this to the graphs. Now I got to graph this guy. Okay, you can plug it in your graphing calculator, right? But remember, it's still, what happens is this 7, this moves it up and down vertically. This moves it left and right. So it moves, so you have your basic parabola, which is moved up by the 7, because at time t equals 0, v is 7. So that's your initial velocity. And then the 16 moves it left to right. This happens to move it to the left. So what this looks like is a parabola, but it looks like this. It goes up. Okay. So it's a parabola that's been moved up and slid over. Now, we know that second quadrant stuff is not real, not for physics, maybe for math. But so we have to kind of do that as a dot, 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 okay? So that's the way that graph looks. And then the next sheet we're going to do, if you look at 410, it's playing with this kind of stuff. This is a preview of the next one. And then the next one's easy, 24t plus 6. Starts at 6, goes to the slope of 24. And then the last one stays at 24. Okay. So that's the quartet, the pink quartet. Now I want you to derive the pink equations. What time we got? We're still good. So let's derive the pink equations. Here. Okay, so I want you to derive the pink equation. Now, I don't like to give you an equation, just give it to you out of the blue, and you get to take it by faith. But I mean, our theme to our class is Nullius in Verba, which is the theme for the Royal Society, the original Royal Society, and it means not by word of mouth. In other words, you're not going to believe me because I tell you something. Just because I say it, you believe it's true. That tends to get you in trouble, science-wise and politics-wise. So I want to offer proof to everything I give you. Well, I'm going to violate that rule temporarily here. When we do integrals later, when we do antiderivatives, and people like Brandon would know this if he's already taken calc. We'll do what's called antiderivatives, and then you can see it. But for now, I'm just going to have to give it to you. So here's the first pink equation. These are the pink equations. And these are now hanging up in the room. So the first pink equation is x of t in general is 1/6 j naught jerk times t cubed plus 1/2 a. And if you remember way back to when we were doing these things, you're looking at patterns and the beautiful patterns. 1/2 a naught t squared plus, then we go down to what's next? Just v naught t plus x naught. So that's the original, that's the position equation for pink. Now what I want you to do is, I want you to, remember when we derived the second orange, it was 10 steps, 10 laborious algebra steps involving substitution and isolation and all the stuff we had introduced. And then we derived the third orange, and that took all this work, another 10 steps. But the cool thing about the power rule, it reduces your derivation down to one step. It's one step per. So give me the equation for velocity in the pink. Give me the equation for acceleration in the pink, and then give me the equation for jerk in the pink. Okay, I'll give you a minute to do that. So take the derivative for each one of those. And notice when I say not, I mean initial conditions. So if I'm reading, well, we'll get to that. I want you to be able to read an equation and interpret that equation. Like read an equation and don't just see the graph in your head, see what's happening. Visualize what's happening. A car speeding up, a car hitting a tree, or whatever, somebody, running a football action, and you go, I know the equation for that. Or I got a feel for the equation for that linebacker slamming into that, wide receiver. Okay, it'd probably be a jerk or a snap situation. So in this case, we bring it down, bring the 3 down, 3/6 is 1/2. So I have 1/2 J naught T squared plus, that 2 comes down, so it's just A naught T plus V naught. So notice that in the position equation, there is hidden, there is a hidden jerk. There's a hidden jerk. There's a hidden acceleration. There's a hidden initial velocity. And then that's not really hidden, but there's the initial position. Same thing with the velocity equation. Let's do it again. That's just J naught T plus A naught. And finally, that's just J naught. So there is that's hanging in my room, the 4 pink equations. So check it out. Okay, so let's try this example. Suppose on our pink equations we have x equals x of t equals 5t cubed plus 3t squared. Here we go. Plus 3t squared plus 6t plus 7. All right, now tell me, what is the acceleration? What's the initial jerk? Just from looking at the equation without even doing any calculus. What is my initial jerk?
5.
Not 5. You're on the right track. What's my initial acceleration? What's my initial velocity? And what's my initial position? So all from looking at that equation, you can get all 4. So let's start with the easy one. X naught, right? X naught is 7, whatever, say meters. V naught is right there, 6 meters per second. What's A naught though?
6.
6, because going back up here, that 3 represents 1/2 A. So A naught is 6. So this object is not only, it starts at 7 meters, it's got initial velocity, you pick up the action, it's already moving at 6 meters a second. It's also accelerating positively at 6, so it's speeding up at 6 meters per second squared. And then what is the jerk?
So 30.
30, right? So this is this would be a crazy, you're not going to survive this thing. You got a jerk of 30. A human cannot handle a jerk of more than 4. A roller coaster, there's things called jerk meters on like roller coasters and subway trains. And humans, I think it's like 2.5. If a jerk of 2.5 meters per second cubed, don't quote me on this because it's been a while since I've read about that. But that's, humans know. It becomes extremely uncomfortable. So a jerk of 30, I don't think so. You'd be in a hospital. If not, worse. All right, so that's an example of interpreting cubic third order polynomials and pulling out the physics out of them. What's really happening.
How did you get 30 again?
Because that first one, if it's a third order polynomial, whatever's multiplied by the t cubed, that represents 1/6 of the jerk. Yeah. So then in other words, 5 equals 1/6 times jerk, or jerk over 6. So then jerk must be 30. So that's not a very, that's nice, looks nice mathematically, but it's not very comfortable human-wise. Okay, still got 7 minutes. The last thing I want to do is look at the back of 4-9. And your homework is, the one I want you to do on your own is this number 3, A through F. It's a little tedious. I'll let you do it homework. I want to do the harder one and more interesting one, which is number 4. So let's get as far as we can on 4. 4 is pink because 4 involves the quartet, pink equations. Oh, and before we do that, right here. This goes back to what we talked about back in like late October. We still coming back to the same themes, and we'll do that again. And you'll do it in AP Physics. You keep coming back. These things don't go away. Okay, I'm not just whistling Dixie. I mean, I'm giving you stuff that we're doing. You're going to have to use again and again and again. These are all, everything I do is foundational. So there's that. Remember we said back then on a quartet, we said that X equals K. I just said KT cubed because I wasn't about to get in, but now we know this is actually, if that was the only one we had, it's really X equals 1/6 J naught T cubed. So the K there, the placeholder, is actually 1/6 jerk. But I couldn't say that at the time without you saying, that's magic. It's still a little magic. I mean, I admit. And then here, the K, in this case, the K is, that's 1/2 A. Okay. So it is a little magic, I admit, because I kind of gave you the first pink. But once we do integrals, it won't be magic anymore. Okay, back to this. Let's do as much as we can in 5 minutes. Try and get A, B, and list A and B done. Maybe start off with C. But this is not homework. This is class. All right, so we're still on the trio. We're still on the quartet here, and the pink. So X equals 5. There it is, 5T cubed. That's weird. That's almost the one I just did. I guess it was in my mind from this morning. Okay, so what is the function of the velocity? So in this case, you can do it with me. This is just X dot. So that's going to be 15 T squared minus 6T, and that's it. The 7 gets lopped off because it goes away. There is no slope of a constant function. So that is, and it's okay, meters per second. I have to assume time is in seconds. And then what is the function of the acceleration? Do it again. So V dot is A of T, and that is 30T minus 6 meters per second squared. And then it says, what's the function of the jerk? Okay, J of T is A dot, and that's just 30 meters per second cubed. Okay, then we're supposed to determine the instantaneous acceleration, the average acceleration, but I got 3 minutes. Okay, well, let's do C. We'll do C and then we'll stop. C is to find the acceleration at 2 seconds and acceleration at 4 seconds. So, okay, easy enough. A of 2, A of 4 is 4 times, it's 120, right? 120 minus 6, 114 meters per second squared. And then A of 2 is 60 minus 6, so 54 meters per second squared. And then we're supposed to plot it. So let's hold off on D and E. Remind me, we'll start here on Thursday. Tomorrow is blue day. Start here Thursday. And so the homework is number 3 when you do on your own. Okay, on the what I want to show you, what I showed the class was on the Facebook group. You guys are more familiar with the Facebook group. A lot of those kids don't go there because they just go to class, but you kind of need it. But on the Facebook group, it has the take-home test, and each problem, this is on Unit 3, each problem is separated. So you can start working on those. You can pick and choose which one you want to start with, but you can do it down through about number 9, maybe. And then you gotta wait till Thursday to do the rest. Thursday, Friday. Okay, so stop the sharing. All right, so we've got a minute here. Anybody got a question before we call her good?
What
Okay.
time will the flex day Zoom start tomorrow?
Good question. It starts at 1 instead of 1:10. And it ends, though, the bad news is 1. The good news is it ends at 1:25. So 25 minutes. We'll spend the whole time going over. So have out, maybe print off another copy for yourself or split screen it. Have not the take-home test, have test 4A out so you can look at it at the same time. We're looking at the problems. And then you'll also be able to, I guess maybe I'll post that. You know what? I'll record it and I'll post that for those kids that missed my class for tomorrow for Flex Day, maybe. So I'll definitely record it because I know some students are trying to do two fifth hours at once. So they have no choice. They have to miss. And then the other teacher doesn't tape. So they have to go to English or whatever. And then they have to watch my tape. Okay, so yeah, that's tomorrow, 1 to 1:25. Okay. We will pick it up there then. Until then, I'll see you guys maybe tonight at the ACT. Bye-bye.